The research paper, Optimizing Hard Prompts with Few-Shot Meta-Prompting, focuses on enhancing the efficiency of large language models, LLMs, by optimizing their prompts. An iterative method is proposed to generate better templates using the LLM itself, without revealing the context. This approach involves few-shot sampling methods to evaluate the effect on iterative propagation while maintaining linguistic styles and syntax. The results demonstrate a 103.87% improvement using the best-performing method, showcasing the LLM's ability to maintain syntax while learning to replicate linguistic styles. The paper examines the dynamics between LLM outputs and linguistic inputs, emphasizing the importance of prompt engineering for optimal performance. Large language models, LLMs, rely on coherent hard prompts to generate accurate and relevant responses. However, optimizing these prompts can be challenging, often resulting in incoherent sentences or task-relevant prompts. To address this issue, researchers propose leveraging LLMs to improve upon prompts used for the same models, exploiting techniques such as mutating prompts and optimizing prompts through chain-of-thought prompting. The authors present two methodologies for iteratively generating metaprompts for multiple tasks, including question answering, summarization, and dialogue summarization. These methods are tested on ChatGPT 3.5 Turbo with a temperature of 1 to maximize diversity in generation. The regeneration process consists of two components: the feeder method, which determines how initial prompt templates are fed to the LLM, and the propagation method, which decides how subsequent prompt templates are fed to the LLM by sampling from a set generated by the LLM in the previous iteration. Two types of feeder methods are employed. Feeder method A, FA, samples the top-n manually written prompt templates with the highest scores based on a dataset D and metric M, whereas feeder method B, FB, samples both the top-n and bottom-n manually written prompt templates with the highest scores. The performance of each method is evaluated in terms of its ability to maintain diversity without stagnation. By iteratively generating and refining prompts, these methodologies aim to create more effective and coherent hard prompts for LLMs, ultimately enhancing their performance and reliability. The authors investigate whether a large language model, LLM, performs better when it knows the type of examples to avoid, examining the effect on diversity by providing a mixture of the best and worst performing prompts. Two feeder methods, A and B, are employed to compare the impact of the prompt set S1 on subsequent iterations for the same propagation method. The authors also explored two propagation methods: PA, which concatenates all prompt templates generated before the current iteration and uses the combined set for the next iteration, and PB, which concatenates the sets and continues using the feeder method to sample prompt templates for the next iteration. The increasing size of the meta prompt with each iteration leads to a context limit, restricting the experiment to 10 iterations. Starting from a manually written set of prompt templates SM, the feeder method samples the initial prompt templates S1 for the propagation step. The propagation step generates and samples results for further iterations, logging prompt templates and their corresponding ROUGELF1 metric scores. The list of prompt templates is ranked best to worst according to their scores, and the meta prompt includes instructions to generate optimized prompt templates along with the sampled prompt templates as few-shot examples. The experiment evaluates the effects of combining different feeder and propagation methods, examining 4 possible combinations outlined in Table 1 and visually depicted in Figures 69. The set S1 for methods employing the same feeder method remains identical, and the prompt optimization pipeline is assessed for multiple tasks: question answering in context, summarization, and dialogue summarization. These tasks are evaluated using the mean ROUGELF1 metric score across 10 data points from the Stanford Question Answering Dataset, CNN, Daily Mail Dataset, and Samsung Dataset, respectively. An extended experiment using 42 data points for the best performing methods is presented in Appendix A, providing further insight into the optimization extent. Results are compared quantitatively, with prompt score pairs available for each batch corresponding to an iteration. The mean, maximum, and similarity scores are evaluated, with the baseline being the set of manually written prompts, SM. Figure 10 shows the mean score results, indicating that methods using propagation method B outperform both the manual prompt's performance baseline and the methods using propagation method A. Notably, method D, despite starting with a lower mean score, outperforms A and catches up with C, suggesting that the propagation method is more crucial than the feeder method or initial set of prompts. To assess overfitting and loss of diversity, a similarity check is applied among each batch of prompts using sequence matcher, yielding a similarity score between 0 and 1. A drastic drop in similarity scores is observed in the first few iterations for all methods, with methods A, C, and B showing similar scores at the end of 10 iterations. The comparison of mean scores for all tasks across different methods highlights the significance of interactions between feeder and propagation methods in optimizing prompts, particularly for question-answering tasks, where a 103.87% improvement is observed over manual prompts. The study emphasizes the importance of defining evaluation metrics for a fair comparison and suggests that negative metaprompting might not be effective if the model focuses only on positive examples. The comparison of mean scores across iterations for question answering, summarization, and dialogue summarization in Figure 10 indicates that methods A, B, and C have significantly lower similarity scores compared to the manual baseline. This suggests the large language model, LLM, may be favoring a select few prompts, learning from and propagating them. Figure 11 shows the similarity scores over iterations for the same tasks, highlighting method C as the most effective in optimizing prompt templates. This optimization is crucial for maintaining diversity in generated responses. The findings imply that the LLM's selective emphasis on specific prompts leads to lower similarity scores, emphasizing the importance of optimizing prompt templates for diverse and effective responses. The study's results could be generalized by extending the experiment to multiple LLMs and different combinations of feeder and propagation methods, providing insights into the interaction between these methods and the LLM. Future work involves exploring these interactions to develop more effective and diverse language generation systems. In the extended experimentation phase, we evaluate the top-performing methods from previous experiments on 42 random data points to assess the robustness and extent of optimization. The results are presented in terms of mean values, maximum values, and similarity scores, accompanied by visualizations of the optimization process. Notably, the ROUGELF1 score of the best-performing prompt in the optimized batch surpasses that of the baseline manual prompts, indicating an improvement in the mean score of the batch. This demonstrates the large language model's, LLM, ability to derive insights and optimize prompts effectively, showcasing its capability to enhance the quality of the generated text. The visualizations provide a comprehensive understanding of the optimization process, highlighting the model's robustness in adapting to varying data points. The mean values, maximum values, and similarity scores offer a quantitative assessment of the optimization extent, underscoring the significance of the LLM's optimization capabilities. The authors present a comparative analysis of maximum and mean scores for two tasks: question answering and summarization, in an extended experimentation setup. This analysis is based on 42 data points. Figure 12 illustrates the fluctuating but generally increasing maximum scores across batches as the number of iterations increases, suggesting model improvement with more training data. Table 4 provides a detailed breakdown of these maximum scores, showing that the summarization task consistently yields higher maximum scores than the question-answering task, indicating better performance in generating summaries. Figure 13 compares the mean scores of each batch over iterations for both tasks, displaying an upward trend with more variability. Table 5 offers a detailed view of these mean scores, revealing that the summarization task tends to have higher mean scores than the question-answering task, suggesting that the model performs better in summarizing text. Overall, these findings indicate that the model's performance improves with more training data and that it is more effective at generating summaries than answering questions. These insights are crucial for understanding the model's capabilities and limitations, which can inform future improvements and applications. In task-oriented dialogue systems, managing prompt diversity and optimizing performance through iterations is crucial. A comparative analysis of similarity scores and maximum scores for different methods reveals valuable insights. Method CFAPB exhibits lower similarity within a batch of prompts, indicating its ability to promote diversity and reduce overfitting of linguistic style and syntax by the large language model, LLM. This suggests that CFAPB is more effective in mitigating the LLM's tendency to replicate existing prompts. The maximum score analysis reveals a mixed trend, with half of the methods improving over iterations, while the other half declines. Notably, methods employing propagation method B demonstrate better performance, implying that sampling a few prompts with their scores each iteration is more effective than sending a consolidated ranked list of prompts with their scores. This highlights the importance of iterative refinement in optimizing the dialogue system's performance. Table 10 showcases the evolution of prompts from the initial manual prompt to an improved prompt from the latest iteration, demonstrating the system's capability to adapt and refine prompts based on feedback and iteration. This adaptability enhances the dialogue system's performance, underscoring the significance of considering both similarity scores and maximum scores when evaluating the system's efficiency and adaptability. The comparative analysis provides insights into the effectiveness of different methods in managing prompt diversity and optimizing the dialogue system's performance through iterations. It emphasizes the need to consider both similarity scores and maximum scores to ensure the system's efficiency and adaptability. In the realm of natural language processing, a comparative analysis of maximum scores across iterations for 3 distinct tasks: question answering, summarization, and dialogue summarization is presented. The findings are elucidated through figures 15 in tables 7, 8, and 9, providing an in-depth look into the performance of various models. The data indicates that the models exhibit varying degrees of improvement and stability across tasks and iterations. For instance, in the question-answering task, the maximum scores demonstrate a gradual increase followed by a slight decrease, suggesting potential overfitting. Conversely, the summarization task shows consistent improvement, underscoring the effectiveness of the models in this domain. The dialogue summarization task, however, displays a more erratic pattern, implying the need for further refinement to achieve optimal performance. This information is crucial for understanding the strengths and weaknesses of the proposed models and informing future research directions. The comparative analysis highlights the importance of task-specific model tuning and the potential pitfalls of overfitting. It also underscores the challenges inherent in dialogue summarization, necessitating novel approaches to enhance model stability and performance. In the realm of artificial intelligence, a system's understanding and generation capabilities are tested through various prompts. These prompts are designed to evaluate the system's ability to comprehend context and generate accurate responses. One such prompt is a game-like scenario where the system must answer a question based on given context to win. This prompt assesses the system's ability to understand context and generate appropriate responses. Another prompt presents a detective-themed challenge, asking the system to identify the person with the strongest motive to commit a crime based on the context. This prompt evaluates the system's ability to analyze complex situations and make informed decisions. A summary challenge is also included, where the system must condense the context into a concise response. This prompt assesses the system's ability to summarize information accurately and efficiently. Lastly, dialogue-based puzzles are presented, requiring the system to summarize the conversation topic accurately. These puzzles evaluate the system's ability to understand and respond to complex, context-dependent queries. These prompts collectively provide insights into the system's understanding and generation capabilities, highlighting its strengths and weaknesses in handling context-dependent queries.